Hello, this is Jeff, and this is going to be an interlude in assembly. This was actually an idea that was requested by a viewer, and the question was around, they're using DOSBox, they're writing x86 assembly code under DOSBox, and they want to just do some simple graphics programming. And I suggested that, mode 13 hex was so MCGA mode 320 by 200 by 256. This was kind of like the easiest thing to get into and to work with. So I wanted to do a really simple program, and we'll just we'll call this GFX8. And the first thing that we want to do, we got to talk about the PC. And again, this is for legacy PC stuff. So this is for things that would have been prevalent in the 1980s and the early 1990s. So if you're looking to write code, assembly code or C code, or some other kind of language, maybe Turbo Pascal or something, in DOSBox, then this would be applicable. For modern, PCs, you have things like SDL and other libraries that you can use. So this would not be applicable in that environment. So, so briefly, the PC of this era, right, had your x86 CPU, which would have been an 8088 or an 8286 or a 386, maybe 486, Pentium 1, something like that. And they all were kind of essentially the same thing, just faster. And as you got up, once you hit the 386, they had enhanced capabilities for multitasking operating systems, preemptive multitasking operating systems, and flat memory spaces. They gave you the ability to move away from segmented memory. But what you're most likely going to be doing in a real mode assembly language program, so like a COM file or even a very simple small mode executable file, is you're going to be working with segmented memory. So the VGA controller is, or I should say the VGA video RAM is located at A000 hex. Now this is the segment paragraph address, okay? And the offset starts from 0, and it's 320 by 200, so it's literally 64,000. So let's bring up my handy dandy calculator here. 64,000 in hex is FA00. So this is the offset range within that segment. Okay. So mode 13 hex. It's 320 by 200 by 256. This is colors, and it's palletized. Okay. Modern displays, modern graphics cards are real color displays. I would say almost predominantly, right? Which means that you're not going to an indirection table and looking up a color and then the hardware displays that. Instead, you just tell the video hardware, this is the exact color combination I want. So this is where things like 16-bit, 24-bit, 32-bit color come in. And, I'm using OS 10. Everything on this display is 32-bit color. And modern GPUs can crunch through those extra large numbers without much problem at all. But back in the day, having you know, a red, green, blue alpha combination where each one of these is a byte, so you have a 32-bit value here. If you had to move 4 bytes for every single pixel back in the day, that wasn't going to work. So in this mode, every pixel is 1 byte. Okay. So the value for that can be 0. Should do this the right way. 2 FF. Right. Those are your possible values. And those index into the palette, and the palette is configured with the red, green, blue pairs, triplets. There is no alpha for this hardware. If you wanted alpha effects, you had to do that yourself. And most games of this era did not do that because you had to read the pixels, you have to do the math, you have to reapply them. It's expensive, right? Some games may have done it for some simple special effects in certain transition scenes, but typically for the game itself, they would not be using alpha type effects. So how do we plot a pixel in this mode? Okay, so in graphics programming, and this is still true today, you're going to hear the width of the display is not always the same as the pitch of the display. Now, in this old hardware, the two are equivalent. So sometimes they're not the same. Right? So in other words, what does that mean? Okay, so let's talk about modern hardware. You would have a width of 320 pixels, okay? But a pixel is 4 bytes in size. So the pitch is equal to 320 times 4, or 1280, right? Because that's how big. The other term for this would be stride. So either of those terms you might see in documentation, or you might see people referring to that, okay? So logically, the display is 320 pixels wide, but physically, it's 320 times 4, or 1280 bytes across. Now, this is just as an explanation here of how we're going to do this computation, because you can take this example and you can apply this to modern hardware. You can apply this to like an STL application, or, you know, probably a whole variety of other things that you might build with modern hardware. But you have to remember that on modern hardware, the stride or pitch of a line or a screen or a texture or buffer is probably going to be different than the actual display width. In this case, so with old hardware, and especially mode 13 hex, the width is equal to, the stride is equal to 320, okay? Because it's 1 byte. So, how do we plot a pixel? Well, the location, I should say, let's just call it offset, is equal to the Y position times the width plus the X position. That's how we compute a pixel. And what we do is we write a byte at that location, at that offset. Now, this is segmented memory. So how do we do that? Well, we have to set the segment register to the segment that we want to write to. And then we need to do a segment prefix when we write our assembly code, and we need to put the byte into memory at that location. So first, but before we do that, we got to go into graphics mode. So the way to do that is, and the assembler I'm using is x86, and x86 will automatically origin this properly and create a COM file for me. I don't have to, it's not like MASM. I don't have to put a bunch of garbage in here to get it to do what I want. So we're going to move H with 0. We're going to move AL with 13 hex, and we're going to call interrupt 10. Now, and then I think before we do anything else, let's do this. We're going to move H with 0. We're going to move AL with 3, and we're going to call int 10. So what's happening here? So this is our start label. This is just for us. It doesn't really mean anything beyond that. We're going to go into mode 13 hex, which is MCGA 320, 200, 256. And then this code down here is going to go back to text mode, which is 80 by, I guess, 25 by 16, right? And technically, to exit this cleanly, there's a DOS interrupt call we should make. We're not going to worry about that for the purposes of this. So if we save this and we run an assembler on it, we should get, yeah, it should just clear the screen, because what it did was it very quickly went into graphics mode, very quickly came out of graphics mode. And I just did that to kind of just level check that the code's okay and it's compiling, and you know we're assembling, I should say. We're going in the right direction. Now, before I go any further, what's happening here? Okay, so first, what's AH, what's AL? So on the old 16-bit CPUs, you had the AX register, and AX could be AH, this was the high byte, or AL, this was the low byte. There's BX, which has BH and BL. There's CX, which has CH and CL. There's DX, which has DH and DL. There's the stack pointer. This does not subdivide. There's the destination index register. This does not subdivide. There's the source index register. This does not subdivide. There's CS, DS, and ES. These are the segment registers. These are the segment prefix registers. These do not subdivide. Okay. So I think I covered everything. AX, BX, CX, DX, stack pointer, DI, SI, CS, DS, ES. These are our registers. Now, these are your general purpose registers. Okay, so these registers here are how you store temporary things that aren't in memory. Now, you can also store things in memory. And so you could, there's an expense to that because, the x86 family did not have like a 0 page, like maybe say the 6809 or the 6502 or the 65816, where there was optimized access to a specific low memory range, which you could almost kind of consider a separate register file that doesn't really exist on the CPU. So for maximum performance, these are the registers you have available to you. So you have 4 16-bit registers, and you have those subdivide into the high and low bytes. So if you're dealing with just bytes, then you can typically use one half of the 16-bit register to do what you need to do. If you're dealing with a full 16-bit word, then you can use one of the 16-bit registers. The stack pointer is fixed in function. It points to the stack, and that's what it's used for. The destination index register and the source index register can be used as temporary 16-bit registers. However, they do have a special purpose as it relates to certain kinds of memory operations. Now, we're not going to get into that too much here, but just know that you can temporarily use them. There is one register I forgot, the base pointer. So, and that's an important register. The base pointer is a 16-bit register. It cannot be subdivided. However, it is it's a special register in the sense that with the BP register, the assembly language or the instruction encoding for the CPU allows for the base pointer register to have offsets that are slightly more complex. The BX register also has behavior around that, where you can do certain kinds of offsetting and indexing with that register that you can't do with others. So that's something to keep in mind. Okay, so we're going to go into graphics mode, right? But here's the problem, right? You think, okay, I'm in graphics mode. How do I write something to memory? How do I put something out there? Well, you could say, oh, well, I know that video memory is at this segment. Okay, so now I'm going to do this, and I'm going to also then say this is kind of assembler specific. So technically speaking, the CPU does not support what I just wrote here directly. The assembler here in this case has a convenience mechanism where it recognizes that I'm trying to move an address into a segment register directly. And what ends up happening is the assembler converts this into, I believe it converts this into a push and a pop, if I'm not mistaken. Actually, it might be a move, a push, and a pop. We'll see. So let's save this, and we'll assemble it. Now we'll look at the list file, which is the file that the assembler creates to show you, what it's doing. So here we can see that this is a lot more complicated than just what I wrote. Yeah, so if you look, the machine code that got generated here, there's actually 2 instructions, not just one. And if we wanted to go one step further with that, we could load up Turbo Debugger on the COM file, okay? And, okay, so see, here's what happens. We can't move the value directly into ES. That's not permitted by the architecture. It doesn't support that as a constant value. And why is that? You might say, why can I move it into this but not that? Well, this just comes again, it's instruction encoding. And so if with the segment registers, they can either so what are we doing here? We're pushing AX to save whatever's in AX. We're moving the value, the constant value, into AX, which the move with AX or BX or CX supports that encoding, okay? We're then moving that register's value into ES, then we're popping AX. So actually to change a segment register is kind of expensive on this architecture because we have to go through behind the scenes. x86 did this work for us. And so sometimes you'll look at assembly code from this era and you'll see macros, especially like in MASM. I don't believe MASM will do this automatically for you. So you'll often see macros, right, that will do this combination of instructions for you. So that's something to keep in mind. If you try to transliterate the code exactly as I'm writing it here, unless you're using x86, it may not work exactly as you're expecting. So I'll just make a note here. MASM's probably pretty dumb and needs a macro. Okay, so just remember that. And I haven't checked MASM in years, so it might be that MASM does this too. Right off the top of my head, I don't know. So Now we have the ES register, which is a segment register. And remember, there's the code segment, data segment. There is the stack segment, but again, we're not really doing anything where that needs to be different. And then there's the extra segment register or extended segment register, whichever particular document you happen to read and how they refer to it. Extended segment register or extra. Think of it in a variety of different ways. So again, segmented memory it sounds more complex than it really is. There's a prefix value that moves through memory 16 bytes at a time, and of course any multiple of 16 is a valid segment register, and I mean or segment value. And just to verify that that's the case, if we divide this by 10 hex, right, we get 2560, right? So that's the number of paragraphs to get to that location in memory, okay? And paragraph is 16 bytes. So that's all a segment is. It's just a special way of dealing with limitations of the hardware at that time. And the way to think about segments is that you're indexing into memory, and then you have an offset from that location that can always be 64K. And segments overlap, but don't let that confuse you. In practice, they almost never do, okay? And the reason that segments could overlap is because of memory allocations for hardware interfacing reasons. Again, practicality-wise, in the DOS world, segments almost never overlapped. And if you're allocating memory or you're dealing with memory in a segmented architecture, you can very easily write your code so that your segment start address is always, at the end of some other segment so that they don't overlap. Anyway, the video hardware is fixed in memory, and it's at this segment. So now let's just do something really, really simple. Let's just put a pixel right into memory. So how would we do that? Well, so we have the ES register set. So now we want to do an ES move. Now, what is this? This is what's known as a segment prefix on the instruction. So again, the machine code on the x86 allows you to tell certain instructions, essentially any instruction that would access memory, hey, this is the segment register I want you to use when you access memory. And the CS segment, which stands for code segment, is implied. So within a COM file in the tiny or small memory model, which is what we're using here, your move instructions, add instructions, inc instructions, sub instructions, mul, div, and all that, they're all going to assume the code segment by default. And in this model, CS is equal to DS is equal to ES is equal to SS, right? They're all the same to start with. But that you can change those, right? You can change the data segment, you can change the stack segment, you can change any of them, and there's really no limitation there. The only limitation that the COM file model has is within the code segment itself, but even there you can load code into different areas of memory and jump to them, and you can do all sorts of cool stuff. So anyway, by doing the prefix, right, we're telling the CPU, okay, this is the segment, and then we're going to offset from that location, okay? Now, how are we going to do this? We need a pointer, don't we? Just like you would in C. So what we're going to do is we're going to move BX with 0. That's our offset, okay? And we're going to use brackets. What does the bracket mean? Well, the bracket means that I'm going to index. Okay, if I just refer to the register itself, then I get whatever value is in the register, in this case 0, okay? So there's no special meaning there, it's just a number. And remember, a 16-bit value could be 0 to FFFF. But if I put the brackets in front of it, what that's telling the assembler is, hey, I want to treat this value like a pointer into memory. And literally on a segmented architecture, what we're telling the assembler is, I want this to be a pair, right? So in other assemblers, this is what it looks like, typically, right? It's segment, colon, and then the offset. Now we want to plot a point, so we're just going to write some value. I don't know if I can do, I don't think so. We'll move AL with 7, and I'm not sure if 86 is going to, yep, I took it. Oh, no. Okay, so BX is our pointer within the segment, and remember, 320 by 200 mode doesn't quite eat up an entire segment. It's not 65535 bytes, it's 64000 bytes. So it fits, right? FA00 was our range, right? Well, that will fit very nicely inside of this 16-bit register. So that means we can address every single pixel on the screen. And I just moved the color value, the index value, into AL. I always forget if, yeah, no, it doesn't like that. You can't use a constant there. You know, one of the things you run into with assembly language is where you can use constant values and where you have to encode registers, because again, you have to remember that memory was a premium, and even on modern processors this is true. So it's much cheaper memory-wise to encode registers, because there's a limited set of them, than it is to encode random arbitrary 16-bit constant values. So in this case, we have to put our color value in a different register so we encode the register pair. Now, I actually kind of prefer x86's approach to segment prefixing, because technically this is really what the instruction set looks like. It doesn't look like the other thing. The other thing is something that I think Microsoft mostly pioneered in syntax. I don't even think it was an Intel thing. Maybe it was. I think it might have been an Intel thing, but yeah, you'll see the other one with the segment, colon, and the offset. Now what we're going to do is we're just going to take off the code that puts us back into text mode. Instead, we're just going to run this, which I'm going to have to restart. That's okay. Okay, so if you look very carefully, there's a pixel in the upper left corner. Now we're going to do something a little bit fancier than that, because that's, I actually have a program here, VidFix, what's it called? FixBit. There we go. Actually, let me do this. I'm going to copy FixBit up to my GFX. There. Now we have a little program that will just take us back to text mode, so we can kind of futz around without losing our display. Okay, so we plotted a pixel, but it's kind of worthless, right? This is not an X and a Y. So let's think about it. The X can go up to 320. Now, bad thing about that is 320 is greater than 255, but our Y can always be within an 8-byte value. But, you know, To do multiplies, we have to use several registers. So what we want to do is we want to get an offset value, which again was this equation here. It was y position times 320 plus x position. So let's do that. Let's figure that out. So if we move let's use AX and we'll move AX with what's 320, 160, and we'll move and see, it's a real bummer that we have to burn so much here. So let's see, can we get to 320? So can we get, what is 160? Ooh, what's 80? Yeah, so I'm just trying to think if there's a way we can shift to it. Because again, you don't have to necessarily use the CPU's multiply. You can shift to get values that are close. But not all values can be, you can't shift to a multiple of 2 and then, or a power of 2 and then get to the other. So if it's 320 by 256, it'd be 64. I don't think we'd be able to do it cleanly. So we'll move AX with, this will be our X position. Or actually, let's make this our Y. Yeah, why not? Make that our Y position. And then we'll do CX, and that'll be our X position. So we'll just put that right in the middle. Okay. Now we have to multiply. So the mul instruction is AX times the register we pass. So if we pass CX here, this is actually going to update AX with the result, and DX, I believe, is touched here too. I'd have to look at the instruction encoding information again. I'm pretty sure mul touches DX as well, but we're going to ignore that for now. So what's going to happen is we're going to multiply. Oh, and actually this is wrong, right? So we got to do this in 2 steps. So first we want to, this is our stride width, the screen, right? So we're going to multiply the Y position times the stride width. So now AX is going to be 320 by 160, 51200. Okay. Now we just want to add X. So now we can just add the X position. So actually we wanted to say this was 100 and the X position was that's our X position, right? So then this is kind of wasteful, so we could just do this with B, but see, we can't do it with BX. This is where things get fun, right? Because the mul instruction is implicitly AX times the register that you pass, and so AX has the result in it. So unfortunately, we have to then move AX, BX with AX here, because we can't index into AX like this. We can only do this with BX or BP. Now, at this point, AX and CX are free again, right? We can do whatever we want with them because we use them to get our BX value. So if I did all this right, A, it should assemble, but B, it should put the pixel right in the middle of the screen, which it does. Okay. Now, you want to draw more than that. You want to draw a line, you want to draw a box, you want to draw whatever. Circles and arcs and things, those start to get more complex. And arbitrary lines, meaning from any xy point to any xy point, the Brensham line drawing algorithm, can be converted obviously to assembly language. It's, I would say it's like an intermediate level task to do that. However, drawing horizontal and vertical lines is actually very easy. You can also draw exactly diagonal lines in either direction very easy because you can just step on X and Y. It's when things are not, corner to corner exactly that the line drawing algorithm has to be more complex. Okay, so now we've got this code that puts a pixel on the screen. But really we would like to have a function, right? So how can we do that? Well, let's copy this block of code and let's move it up here. And so now we have a function that doesn't take any arguments right now. Actually probably should take the comment with it. And if we just call plot, right? So what did I just do here? I created a label. I moved the code that we just had up underneath that label. So what is that? I just moved it in memory, essentially. This just keeps track of where in memory that happened to be. Why did I put this jump start here? Well, because this code can't really run yet. So what I'm doing is I'm jumping over all these definitions to start, and then this code is the code we want, right? This code puts us into graphics mode. This calls our pixel plotting function, which right now is not parameterized, but we're going to get there. And then this code, which we'll eventually put back in, would take us back to text mode, okay? So let's assemble that. Let's run it. Oh, and it hung up. That's okay. We're going to definitely have to, I keep doing that. I'm going to have some mistakes here, right? Okay, so what did I mess up? Well, let's do this. Let's run it through Turbo Debugger, and well, let's just run it. Well, actually, okay. I terminated. So the very first, I have a jump. The very first instruction, which jumps to 011D. Which is 011D is right here. And then we call back up to 0103, which is right here. That's interesting. Where'd our jump instruction go? So I'm just going to check so at address 0100, which is correct, this is the origin, the default origin for COM files. we have a jump start. Jump start. And then we jump down here to start, which the very first instruction is at 011D. And then we call plot, and plot is at 0103, which I think that might be actually. So the even instruction, what does that do? Or the even directive? If we look at the graphics list file now, we should see that, we should see that the assembler burned an address for us, and the code itself actually now starts at a word boundary instead of at an odd location like this. And occasionally, again, alignment is something that you have to keep in mind, but we're still locked up. So what's wrong there? What did I do wrong? Let's see here. Oh, yeah. Okay, that might be. Oops. Helps if you can type too. I don't know that would be an issue, but it might be. No. Okay. Good thing that restarting DOSBox is easy. Huh? All right. Let's see here. Well, let's do this. Let's take the call out. Nope. Boy, it really doesn't like that. Oh, different directory. No, so it's not alignment. What's going on? That's bizarre. What did I do that was silly? Silly Willy. You know me. Okay, it doesn't need that. I'm really confused. Okay. Weird. There's something address related there, and I'm not really sure. I thought I saw that the alignment wasn't that bad, but okay. Well, the real test will be, unless I did, yeah, I must, I don't know. Okay. Anyway, I'm gonna have to revisit the mystery of what I messed up there. So we have the start. We don't have to do the jump anymore because this is the actual code we want to run. So, and I just moved the function to the end of the file. The only thing I had to do there then is I had to make sure that when we fall through here, I have to make sure the AX register is 0 and then call it ret, because this is the end of the program, and we have to essentially give control back to the operating system here. Now this is again not officially the right way to do this. There's a DOS interrupt that you have to call to, you know, tell DOS the exit code and things like that, but this works in a pinch. And so this is our plotting function. Again, I would normally have this up above and I'd have the start code below, but that's okay. This works. I'm not sure why that jump wasn't working. I have to look at that again. It probably something was really simple. I'm just not seeing it. So we want to parameterize this. So how would we do that? Well, again, we obviously don't have a lot of registers. We have, you know, 4 general purpose 16-bit registers. We have, you know, 8 8-bit registers. But you can see here, we're pretty much working with 16-bit values for the most part, with the exception being the color. So the way we would do this is we would pass values on the stack. Now, I'm going to put an underscore in front of our plot function here, and I'm going to make a macro. And in x86, you give the macro a name, you use the macro identifier, and then the end of the macro block is a #em. Syntax is a little strange, but you get used to it eventually. And then in this case, what we want to do is we want to take some parameters that are going to come into the macro. Macro parameters are just #1, 2, 3, 4, 5 up to, I believe, 20 or something. And those just get substituted as text. There's no magic or anything that happens there. Whatever the value of the macro parameter is gets inserted into the macro in place. And so what we're going to do, what we're going to want to do, is we're going to want to push our parameters here. So we know, and again, the stack on these CPUs, well, the 8088 and 286 and in real mode, it's a word size stack, so 16-bit values that you put on here. So we want to push the Y position, the X position, and we want to push the color. Now, unfortunately, the color is this is going to burn an entire 16-bit value. If we had some other parameters, you maybe could combine them, 2 bytes into a word. Sometimes you can do that. In this case, we're not going to be able to get away with that very easily. Then we want to call our plot function, and that's it. And then the only thing we have to do is we have to clear off the stack. So we have 246 bytes, right, that needs to come off the stack. Why 6? Because again, 16-bit value is 2 bytes each. So 246 bytes. Adding to the stack pointer frees memory off the stack. Subtracting from the stack pointer gives you memory, allocates memory from the stack. So this is an example of how you would call a function like this, passing parameters in. Now, within our plot, what we need to do here is we need to move the base pointer with the stack pointer. So why do we have to do that? Well, because we can't index the stack pointer. We can't do anything fancy with it. We can't treat it like a structure directly. The CPU just doesn't support those kinds of encodings. So here we're using the base pointer to do that, to allow us to get to certain points within the stack directly to get values out. Now, it just so happens that x86 has a pretty nifty feature where you can create a structure. So we can do a struct, and we can tell it that it's a BP-based structure. And the ends statement ends the structure definition. Now, the very first value is a burner value. It's the return value, actually, that's on the stack. We don't care about that. We don't want to touch that. Then we want to actually have, this is going to be our Y position. Actually, no, I'm sorry. So this would be color. Wait, I'm pushing, it's going to be YX color. So, yeah, so actually this would be Y position, X position, and color. And the way we can do color is we can do a pad byte and a color byte. So we take that word and we tell the assembler, hey, break it down this way for us, okay? Now, here's the really cool bit. By moving BP to point at the stack pointer, we now have access to these pseudo variables, right? The assembler kind of intelligently knows that I can access things from BP, right? So I can access the Y position this way now, and I can access the X position, and I can access and actually we don't even need to, I don't think we need to load that there. We can just do that directly, right, from BP at that point. Now there's a couple other things here, right? We're starting to stomp on some registers. So we probably want to save some other state, right? So we should probably push BP, ES, AX, CX, DX. We should do AX, BX, CX, DX. If we wanted to save all register state, right, this would be the way to do it. And remember, you would pop them off in reverse order from how you put them on, right? So what this does, what we've built here with this macro is this macro creates this epilog, call, prolog code for us every time we want to call this function, instead of us having to do that ourselves every single time. If we didn't use the macro, we'd have to write that code in every single call spot. And that's error prone. You're going to forget. So now we can plot, this is Y, this is X, and this is the color we had, right? And of course, had to have some errors. That's just how it works. Okay, yeah, I can't do that. See, I thought I could be all clever. Yep. What else do I got? Oh, right. So macros are one of those things in x86 that does have to be defined in order. in general, most assemblers are not order specific. Some parts of them can be, right? In this case, macros, the macro actually has to be defined ahead of time. So in that sense, it's kind of like C. The macro has to be predefined, but the code actually, the labels don't, because that gets fixed up later. So we call this, did we get our pixel? We didn't get our pixel. So let's take a look out, and you know, guaranteed I got the stack order wrong. So let's see, we're pushing, so Y, X, color, return value. So it's color X, Y. So it's return value, color X, Y is the order. Maybe not. Okay, so let's do Turbo Debugger. And let's come right here. Okay, so you see here we're pushing our values and we're making our call. And so the call is going to be down here, right here. So let's put a breakpoint right there. Let's call it. Okay, and we're going to step, and actually let's, that. Okay, so we're moving ES with the right segment, and that's correct now in the debugger, right? And now we're going to load from BP plus 6. So BP, if we come down here to our data thing, we can go to BP, and we can see, okay, so here's what's on the stack, essentially. So 1, 2, 3, 4, 5, 6. So it's FB. So if we go back in our code view, what did we push? That doesn't look right. We pushed 64A0 and 007. So if we look down here, where's 64? I'm not seeing it. So what's BP? BP is pointing at FFEA, and the stack pointer is pointing at FFEA. So it's like something clobbered our stack value, maybe. So 64 A0, yeah, I'm not seeing those on the stack. Well, actually, they are over here on the stack. Oh, okay. My bad. I got that backwards, didn't I? So BP is pointing, okay, yeah, so on the stack, so it's 1, 2, where are we at here? There we go. Okay. So there's 64, there's A0, there's 07. So these are 16-bit values. So, and this is actually the return address of where we're going to go back to. So this is where we're at right now. So we're going to go 1, 2, 3, 4, 5, 6. Is A0, which that sounds right. Okay. So we've multiplied A0 times 140. These are hex values. So A0, which should be 160, times 140, that gives us C6C, or 3180. That doesn't seem right, because we have 7000 in, so we had A0 times 0140, C800, there we go. Right, okay. Did I do an add already? No. Yeah, that seems off. Okay, let's do this. Let's stop. Okay. So let's try this again. Okay. So AX is 64. Ah, that's why the values are different. Yeah, that seems wrong. I think I got my order wrong again. Yep, they're backwards. Okay, so let's fix that. So I'm going to guess that these are backwards too. Oh, you know what I got backwards? That, I almost guarantee that's what I got backwards. The color in the pad. Yes. Little endian. Yep. Okay. Except, okay, Y and X are... There we go. Yeah, I had it right, and then I had the pad swapped. Okay, so if we look at this, so yeah, stacks, right? You got to remember that things are backwards, and you got to remember the endianness of your architecture, right? So in this case, the low byte, right, is, or what we would think of as the low byte, as stored in memory in the high position, right? So you have to keep that in mind, and so I made that mistake. So this little dandy here is really convenient, because we could do this the old-fashioned way, meaning that instead of doing Y position here, I could do, you know, I could figure it out. I could say BP plus, you know, whatever. So it's be 2, 4, 6, right? I could do that myself. That's a way of doing it, but this is much, much nicer because you can refer to these things with names. And again, MASM has similar features with structures and offsetting. It's been a number of years since I've used MASM's features. I'd have to review those again, but the principles are the same. And again, behind the scenes, what's happening is the assembler is just saying, oh, okay, this variable is in this structure. And by the way, these symbols here are global. So they have to, in this assembler, these symbols have to be unique. They can't be, they're not namespaced, right? So technically I probably should be calling these plot color, plot pad, plot X, right? So that if I had other things in the future, they would not, you know, collide with this set of variables. And so that's how the assembler, it's just matching the unique symbol and saying, oh, okay, I know what this structure looks like. I know how this is supposed to work. So we've taken this function, or taken this code that used to, you know, plot a pixel in the screen in a fixed position. Now we've moved it into a function. It takes parameters on the stack. It saves the stack state, or saves this register state to the stack as well. Now, this is a lot of registers, right? This is a lot of stack manipulation. Now, this is uber safe, but, you know, you might be able to optimize some of these away. You probably definitely want to save and restore ES. You maybe want to save and restore some of the other registers. I'm doing the most safe thing here, which is just saving all state and restoring all state. But you can optimize that as you need to. And again, it's based on, you know, you're going to know what you need to do within your code to make this work. Now, because we're saving all that register state, that means that in the call site where we're using this macro, we essentially have all of our registers available to us again. Obviously at a little bit of a cost, right? Stuff's being put on the stack, taken off the stack to make that happen. But what we can do is we can now say, okay, AX, or actually let's even just be really simple. Let's do this. Let's move AH with 0. Let's move AL with 0. And let's move CH with 2. Actually, let's do this. 320 minus 256. 64 divided by 2. No. Yeah, so this would be 32. This would be... actually, let's make this Y. Let's make this X. We'll make CH 250... make CH 200. And we'll make CL 256. And then what we're going to do is we're going to have a label here. Now, again, x86 supports these local labels, which are a single character and a single digit, followed by a colon. And then our color value, let's move BL. Let's use DL with 1. So now we actually should, let's clear out DX. Because again, remember we have to pass a 16-bit value here. We can't just pass an 8-bit register. So this is going to be a, well, will that work? No, that won't work. Yeah, crap. So here's what we got to do. Well, no, that'll work. I can do that. So we want to do, we said AH was X, or Y, rather, right? So AH by 0. This is, again, this is a number, this is AL by 0. And this would be DL by 0. Let's just make sure I'm thinking about that right. Maybe not. Ah. Yeah, I won't do the... Yeah, crap. All right, well, we'll burn. We'll burn some registers. So we'll use AX as Y. We'll use BX as X. So this is Y. This is X. And we'll set, yeah, do that. And then we'll use DX as the color. Because again, these have to be 16-bit compatible values. So YX color, okay? And then what we're going to do is we're going to ink AX, or I'm sorry, BX. We're going to ink DX. And the beauty here is that, well, I shouldn't say the beauty. We're going to ink DL. And what's going to happen is, this is an 8-bit register, it's going to overflow. And when it overflows, it's going to go back to 0. So what we can do here is, actually, we'll just let it overflow to 0. That's fine. This, we're going to increment BX. That's our Y position. We're going to compare that, or actually, we should do that prior. We should compare BX to 320. If it's not equal to that, we're going to go here. So, and that's to the next increment. Otherwise, we're going to come here and we're going to move BX with 0, and we're going to ink AX. And here, we're going to compare AX with 200. And if it is 200, we're going to go to L2. The greater than symbol just means that the jump is ahead of us. It's happening further down in the file. It just kind of is a hint to the assembler so that it knows that it's not behind it. So we have our Y, our X, and our color. We call plot, which is our macro, which expands into those pushes and pops and calls and all that. Passing in the Y, the X, the color. We compare the X value to 320. If it's not 320, then we come down here, we increment the X value, increment the color, and we jump back to L0 here. And instead of jumping to L2, we'll just jump to end here. Okay, and let's see. Yeah, so we compare to 320. If it's not, we increment X, we increment the color. Remember, we're incrementing the lower 8-bit register on that, so which is the only part of it that matters. And that's going to go up to 255, and it's going to roll over to 0. And it's just going to keep doing that, and that's fine. And we're going to jump back up here. If we do equal 320, which means we've hit the right-hand side of the screen, then we're going to reset the X to 0. We're going to compare the Y to 200. And if we've hit the bottom of the screen, then we're going to jump down here to end. Otherwise, we're going to increment the Y position, and then here we want to jump back up. Right. So that's our little loop. And if I did this right, which, you know, oh, it won't do that way. That's fine. And that's what we get. And that's actually correct. That's what I expected to see. Except it locked up. So we gotta figure that out. Wrong directory. Okay. But you can see, right? We're cycling through the color palette and we're moving along the screen. And our plot is... Let's do this. Let's compare. Let's just do half the screen. Ooh, yeah, that's not good. Okay. Something's off. Let's take a look. Let's make sure I got this right. BPES AX BX CX DX DX CX BX AX ESBP. That looks okay. All right. All right, let's do this. Let's just run her through the old debugger. Oh, yeah, so you can see what the macro does, right? So here's all the state we're saving. We're calling our function. We're clearing up the stack. And then we're restoring the state. Okay, so that's interesting. All right, so BX is 0. We're going to increment BX. We're going to increment the color. We're going to jump back up. We're going to do the whole thing all over again. So let's put a breakpoint here. And let's take this one off. Okay, so BX is 140, 320. We're going to reset it. We're going to compare AX with C8. And it's not equal. So we're going to increment it. And then we're going to jump back up. Do that again. Yep. So we're going now, AX, we're going through all the rows. So now what we want to do is, if it's equal, we're going to branch down here. Okay. So now let's take this one off. Okay, so now we're at the end. So I think actually our graphics code's okay. I think it's the way we're exiting now is not right. So this really is the right way to exit this program is AH, what is it, 4C, AL is 0, and then it's int 21, I believe is the correct. Yeah, there you go. I kind of figured that was eventually going to catch up with us. You know, you have to call the correct exit code or exit termination DOS call. But there you go. There's our color, and we're filling the whole screen. And that gives you an idea of how you can loop and reuse that function to populate the screen. Now, let me see. I gotta look up real quick. Let's see. There's a, oh, here it is. This will do it. Okay, so what we're gonna do is, I just looked up, there's a BIOS call we can use to just wait on a key, and that's pretty much what we want, right? So we're gonna put our mode reset code back in, and so what we'll do here is we're going to move AX with 0, and we're going to call int 16 hex, and if the result of that is 0, then we're going to go to L2, right? And this, wait for key press. Maybe. Nope. I was pretty sure that code worked. I probably messed it up somehow. I'm on a roll doing that tonight, so. Okay. What did I do wrong? Dun, dun, dun. I'm going to say, let's look this up. What does it say? Int 16. Yeah, AH is 0, AL returns the ASCII character. If no key is available, this waits for a keystroke if you want to avoid the wait. Right. So, oh, wait, okay, duh. Because that waits, right? Yeah. Yay, there you go. Okay, so, as is typical when I write assembly code, it never works the first time. But you keep playing on it, and, you know, you keep working on it, and eventually it gets where you want it to be. But this shows you how this works. And with this basic approach, you can now build, you could build sprite renderers, you could build tile renderers. You know, most of this is all now relatively very straightforward because you have the basics. Now there's a couple things here, right? Like, do we have to set ES every time? You know, you could optimize this. You could start to pull things apart and maybe make it a bit smarter. So we could move, we could set the ES segment once before our rendering code, right? So maybe what we do here is we push ES, and then we're going to do this rendering code. And when we're done with the rendering code, we pop ES, right? Because we don't need to do that every single time, right? The way, if you were going to write something efficiently, you would probably maybe optimize it that way. Another thing that we could do to maybe optimize it one more way would be, you know, hey, we know we're going to call this thing in a loop, and we're not doing anything with BP inside the loop other than, you know, this plot function, right? So maybe we could push ES and BP here, and we could pop it here, and then we don't, so we're going to do that once before we do all of our rendering for the screen, and then we reset it after, and then we don't have to put that state on the stack every single time we call our plot function. So these are the kinds of things you can do to start optimizing your code, right? Now, what difference does that make? You know, that we're shaving cycles here and there, okay? Probably microseconds. It's not making huge difference, but it, you know, these are things you can do to impact the performance of your code, right? So anyway, I think that covers really the basics. How do you get into mode 13? What does memory look like? What registers do you have available? What's the stack? How does the stack work? How can you use the stack to your advantage to pass parameters, wrap things in macros, so that, you know, this sort of stuff where you have to do your your prolog, your call, your epilog. You don't want to have to do that by hand every single time. So macros are your best friend. MASM has macros, TASM has macros. Their syntax is a little bit different. Read your manual. They'll show you how you use those, but the gist is the same, right? And so again, to look at the code top down, you know, we talked about kind of what memory looks like, how we calculate positions in this mode. I have a macro here that makes a call to our plot function. We have our start for our program. we go into mode 13 through the BIOS. We save the state of the extra segment register and the base pointer. We move the extra segment register with the segment address of the VGA video RAM. AX is going to be our Y position, BX is our X position, and DX, technically DL, so right, the lower byte of DX is, so another way we could do this, right, is we could do, we could XOR this guy, and then we could move DL, right, since we're just manipulating the lower part. So we're clearing out the whole register, we're moving the lower part with, you know, 1. We could do it either way, right? They both kind of accomplish the same goal. This is maybe making your intention just a wee bit clearer. And we call our plot macro, passing in AX, BX, and DX. Again, AX is Y, BX is X, DX is the color. They have to be 16-bit values here, right? We compare our X to 320. If it's 320, then we're going to reset it. We're going to compare our Y to 200, and if we're at that, then we're done. Otherwise, we increment our X and we increment our color. And now what we could do, just as another little quick test, we could move our color increment here just to make it a bit different, right? Now we get some nice striations, because now we're changing the color only when we go to a new line. And there's 200 lines, not quite all the lines we need for color change, for all the colors, but we'll cover most of the palette. Now again, this is the default palette. You can change the palette to be whatever you want it to be. But again, for purposes of demonstration, you know, this shows you, you know, what's happening there. So, right, so if we are not at the right edge of the screen, then we come down here, we increment the X, we come back up here, we plot the next pixel. If we do hit the right edge of the screen, we go back to the left edge of the screen. We compare our Y position with 200. If we are at the end, we come down here, we pop our registers off, we wait for a key press, and we reset our screen to text. And then we call the appropriate MS-DOS exit function so that it doesn't hang. And then our plot function down here is we have a structure here, right, that allows us to access the stack cleanly. And so this very first word is unidentified because it's the return address, right? And we don't really care about that. We're just going to ignore that. Our color is always a byte. And again, this is a little endian architecture, so that byte is actually the first byte in the sequence, unlike what you might think with a big endian would be what you would assume. And so we have the color and the pad byte, and then we have our X position and our Y position. We move BP with the stack pointer, so the base pointer now is equal to the stack pointer. Why do we do that? Because the base pointer in this architecture allows us to index, right? Allows us to do offsetting and things. We move AX with the Y position, right? So by doing this, x86 is smart now, and when it sees this symbol, it says, oh, okay, well, whatever BP is pointing at, that's that location plus this offset, right? And how does it get the offset? Well, this is 2 bytes, this is 1 byte, 2 bytes, so on and so forth, right? We move CX with 320, which is the stride of the screen. We multiply 320 times the Y position. We add the X position to that, so that's going to get our pixel to the right location in video memory. We have to move the resulting AX value into BX because we have to index into memory. We have to treat that as a pointer, and BX is kind of like BP. It's a base, it's called the base register, and it can support certain kinds of pointering and offsetting behavior similar to BP. We could use BP in this case here too, but we're already using BP to deal with the stack. So we're point into video memory because we're doing an ES segment select here, and we're saying we want to write to this offset, we're going to write this color value. And then we're done, we return, and you know, in the macro, that adds 6 bytes to the stack pointer, so we erase all that data, right? This data that we put on the stack, nobody's popping this, it's just sitting there. So this erases that stack frame, and then we pop the registers off that we had pushed on. We went through a cycle where we kind of optimized that a tiny bit and got rid of some of the registers. You know, we're using AX, BX, and DX here, right? So technically we don't have to push CX, although I would say it would just be safe to do that. And that's it. That's all it took. About an hour and a half and a couple of debugging sessions, and there you go. And like I said, now fundamentally you have the code that you need to you can build anything you want on top of that. So anyhow, I think that will cover what I wanted to do in this video, and hopefully that will help folks who are trying to, you know, learn this stuff and build things, you know, in DOSBox with assembly language. And again, the principles here would apply to assembly language. They would apply to a phone call. They would apply to C or Pascal, Turbo Pascal, or even BASIC. I mean, most of what I've described here, the hardware doesn't change, right? The memory addresses don't change. The model in which you access it doesn't change. The language features are different, right? With assembly language obviously being the lowest level, but you know, the way you go about doing it is the same. So anyhow, I think that'll about do it, and thanks for watching. Bye.